Hi everyone, this is David Singletary. This is COP2073C, Introduction to Statistical Programming with R, and this is Module 10. In this module, we'll talk about the Tidyverse. We'll do a little more visualization, brief overview of workflow, and then we'll use the dplyr transformation package in the Tidyverse to manipulate some data. So the Tidyverse is, as this quote indicates, an opinionated collection of R packages. By opinionated, they mean that it's emphatically supported by the users. The user community for the Tidyverse consists of statisticians, mathematicians, non-programmers, and the Tidyverse brings the R language down to earth for that community. And we like to use it because it emphasizes consistency, communication of results, and reproducibility of results. And those are important characteristics in the day-to-day work of data scientists. It's very community-oriented. If you look at the previous slide on these hexagonal tags that represent the various tools in the Tidyverse, if you go to an R conference, these things trade like currency. If you go to one of the conferences, the RStudio conference in particular, everyone's very welcoming. It's a very engaging environment. The instructors are very willing to help, and all the users you interact with are very nice people. So if you get a chance, you should try to attend one of these. If you just Google RStudio conference, you can find information on the latest one. The Tidyverse isn't for everybody. It does have critics. You can read this article by Norm Matloff that refers to the complexity of functional programming. But it serves its purpose, and I think you'll find that the functional programming aspects are really transparent to us in terms of how we use the packages. And the functions we'll be using here are fairly accessible, so I think you'll find that it's not that difficult to use. We'll go through packages provided by Hadley Wickham, who created the Tidyverse, in the data science textbook that we're using for the course. Now, we already know how to load packages with the install packages function, and loading the Tidyverse, using the quotes around the name of the package, and then running the library function to load it in R or in RStudio in our session, specifying the name of the library without the quotes. We only need to install the package once, but when we start a new session, we do have to run the library function again to reload the library that's already installed. You may get version warnings when you're running some of these libraries. When we're loading some of these packages, it'll say built with R version so-and-so, and maybe you're running behind a few minor versions. So if it fails to load, you can update from within an R session. From the console, you install the install R package, load it with the library function, and then run the update R function. This will lead you through some prompts to make sure that you want to upgrade your R version. But I wouldn't recommend this unless you absolutely cannot run the package with the current version that you're using. Sometimes it'll give the warnings of the version, but it'll still run okay. If it absolutely fails, though, you might want to go through these steps, but you don't want to risk breaking the package entirely if you update to a version of R that the package doesn't support. So use this with caution. So let's work through a little problem here. We want to use the MPG data set that's in the Tidyverse, actually in the ggplot package, which is included in the Tidyverse. Our question here is, do cars with big engines use more fuel than cars with small engines? Which is a pretty intuitive answer. The big engines will use more fuel, but we can visualize it to look at the relationship to be more precise. So the MPG data set in ggplot2 is a data frame, but it's actually a little more than a data frame. It's stored as a Tibble. A Tibble is a more functional version of a data frame that's provided by the Tidyverse. If we look at the data here, you see MPG reports as a Tibble. It gives us our column names, and it gives us the data types for each column name. At the bottom, if it extends too far to the right, then at the bottom it says you've got 4 more variables, and it shows those variables, the column headings, and the data type associated with them. And also 228 rows, so we don't see all the rows that are available. So if we look at the difference in what this looks like versus a data frame, let's go to RStudio and take a quick look. So here in RStudio, we'll look at the MPG Tibble. You see, again, reports as a Tibble. This is the column names and the data types on those. If we run as.dataframe with MPG, you see it looks a little different. If I scroll way up, we'll see the column headings. We don't see the data types on these. When it goes to the right past the transmission type variable here, if you scroll down, you'll see it stops at 90 observations, and then it starts back up with those variables that are off to the right. So we'll see all the variables. We're not seeing data types with these. we get 90 observations, and this is a configurable option. You can specify how many lines of things you want to see. In this case, it's 90, and so we miss 144 rows. So we could increase or decrease this configuration option if we wanted to see more or less data. But you see, this is the basic difference in how the data frame looks versus the Tibble. If I run a class on MPG and class as .data.frame MPG, just reports as a data frame. So we've got additional attributes in the Tibble that are associated with it. It still contains the basic data frame attributes as well. So some of the variables in the MPG Tibble are the displacement of the engine, which is the engine size in liters. And then we have highway, HWY, which is fuel efficiency on the highway in miles per gallon. That's one we're going to use to do our little analysis with. So our hypothesis, if you will, is that a car with a low fuel efficiency consumes more fuel than a car with a high fuel efficiency when they travel the same distance. So first off, let's look at a plot of the data of the two variables we're going to track. We're going to use ggplot. Now, if you remember from Module 4, we used qplot. Both of those are Tidyverse plot functions. ggplot is a little more functional. It's more useful when you're writing longer scripts, whereas qplot is designed more for the interactive environment where you're interactively typing these plot commands. And ggplot allows us to add layers to our plots. So the simple ggplot command here, we specify our data. That's our MPG Tibble. And then we add a layer of points. So by using the plus sign, we can add, in this case, a geom of points. We have to provide this mapping variable, and this uses an aesthetic, which we briefly touched on in Module 4. In this case, it's the XY aesthetic, which is mapping the X and Y axes. So we specify the displacement of the engine as our X, the highway as our Y, and this will give us our axis lines along the bottom for displacement with the tick marks, and then the vertical axis lines for the highway mileage with the tick marks there. And then it just plots the points along those two axes. So ggplot provides a lot of different geoms that can be used to add different layers, including various types of lines and other markers. I mentioned the mapping aesthetic where you have the X and Y variables here, and ggplot looks for the variables in your data argument. So we specify the MPG data here, and it's going to go looking for these variables. And you noticed in the plot that it used those variables as the axis names as well when it created the plot. So in the X-axis we had the displacement, and in the Y-axis we had the highway. Now here's how we can do a trend line using our linear model function. We specify ggplot, we're providing the data. Now you notice we've moved the XY aesthetic up into the ggplot function here. And then our geom point layer is much simplified here. We don't even provide the variables. It uses variables provided in the aesthetic in the function, in the ggplot function. And then we can add a smoothed trend line using geom smooth aesthetic, and we provide the linear model function as the function to call. And then we can see we have a downward trend between the displacement and the highway mileage, which means that as you get larger in the engine size, your highway mileage goes down, so it becomes less efficient. So this is a way we can visualize that hypothesis we made that larger engines are using more fuel. We've seen this slide before. This is in Module 4 where we looked at some of the basic aesthetics, and you have these different points, these shapes that you can use, and you can change the size and color. We can map a third variable to an aesthetic. So here we're using the categorical class variable from the MPG data set. And you can see when we run this, we provide the MPG as the data. Now we've moved the aesthetic back down into the point geom, and we're specifying the additional class variable as the color for this mapping. And so we get the different colored points for the different categories of vehicles. And we can see there's some clustering here for the smaller displacement, and then for the larger displacement where the SUVs are occurring to the right side. So we can map the additional variable using the aesthetic, and ggplot automatically determines a level for the variable. So back here, we did not specify what color we wanted for each class. ggplot just automatically assigned a value for each of those levels, and it adds the legend as well, as we saw. We can use a size aesthetic where we change the size of the point. So here we're mapping the size to that class variable, and you see we have all these points with different sizes for different types of vehicles. You can see that it's not very clear here, so this is not an ideal choice for this particular plot of this data. Other things we can do, varying levels of transparency using the alpha aesthetic, and then we have the different shapes. So we've seen for the additional variable we added, we got a legend that shows the different scales and colors for our variables. For the X and Y, we got the axis line with the tick marks. Here, if we wanted to change the value of the color for all the points in our plot, we could use the color argument just like we did back in the ggplot back in Module 4. You have categorical variables like the class of vehicle that we're looking at. You might want to use facets instead of using the aesthetics in a single plot. Facets will create multiple subplots. It'll break everything out for you. And it does it automatically by virtue of the behavior of ggplot. So here for ggplot, we're specifying the data, specifying a point mapping for our plots, but then we're adding a layer with a facet wrap. Combining formula notation, remember formula notation, and you don't have to have the left side. This is single-sided formula. So the subplots are going to be a function of the class. Each class will get its own subplot. And we can specify the layout for the subplots here. So we're saying we want 2 rows of subplots. And then you see we get individual subplots for each category of vehicle. And it's much clearer to read because everything's split out. So we can get a better idea of where those clusters are occurring for the different categories. So this is just drilling down on the facet wrap function, showing that for the facet wrap, you need to specify your formula. In this case, the one-sided formula with our car class. And then we can specify the geometry of the facets or the subplots that it creates. Here we're asking for 2 rows of subplots. And facet wrap is a discrete, in other words, not a continuous number, but a discrete variable, typically a categorical like we've seen. We're already familiar with the formula operator, the tilde. The left-hand side is the dependent, and the right-hand side, which can be more than one variable, are the independent variables, and we use the plus sign to add more independent variables to that expression. And as we've seen already, we don't have to have that left-hand side. If we want to use the facets with 2 variables, we can use the facet grid function. Again, we provide a formula, but now we've got more than one variable, and we're specifying in this case that drive is a function of a number of cylinders. And so if you look at the difference in this plot, we have 2 dimensions we need to look at. We have the number of cylinders on the top, 4, 5, 6, 8. You see there's not that many 5-cylinder cars. And then on the right-hand side, we have the drive type, which is 4-wheel drive, F is front-wheel drive, and R is rear-wheel drive. If you dig into the data set and the documentation for it, you'll see these. And so we get a grid of subplots showing the highway mileage as a function of the drive type on a per-cylinder basis. So we have a 4-cylinder, 4-wheel drive car here, and then mileage for a 4-cylinder front-wheel drive, and apparently there weren't any available 4-cylinder rear-wheel drives here. And then again, not that many 5-cylinder cars, 6-cylinder, 4-wheel, front, and again, I'm looking at the column headings on the right side here, and then the rear-wheel drive, and then finally 8-cylinder, a lot of 4-wheel drives there, and a lot of rear-wheel drives, not that many front-wheel drives for 8-cylinder cars. And so each of these point values is our highway mileage for those categories. So again, this is the facet grid function that allows us to plot multiple variables. We've seen already that a geom is a geometric object that a plot uses for representing data. I have a lot of different types of geoms. If you Google them, you'll find out there's at least a dozen with different shapes, different line orientations, and scatter plots, of course, using the point geom. And we can use different geoms for the same data. You just change a geom, and that will do the different plot types. So here we're doing the point for the scatter plot, and then we can do a smooth line with the smooth geom. So here are examples of both of those, our scatter plot, which we've seen, and then our smooth, a line plot of our points. Now this is similar to the linear regression we did on an earlier slide, but in this case it's not a regression function. It's just a basic smoothing function that plots the point values on the blue line. But you see also we do get the confidence intervals here, also known as confidence bands on this type of plot, that give us a reasonable prediction of where the points can occur based on the surrounding points. But again, this is not a regression plot. This is just a smoothing plot, or what they call a smoother. Now, we don't want to do aesthetics that don't really apply to a particular geom. For instance, we don't want to specify a point shape for a line geom. That wouldn't make sense. So you have to make sure in the context of the geom you're using that you use the appropriate aesthetics. So for a line, we would want to use, for instance, line types. So here's an example of letting ggplot use the different line types available to map the drive type variable in addition to our displacement or engine size and our highway mileage. So we're specifying a line type. This is similar to the color example we did earlier. So ggplot automatically determines which line type to apply to each drive type. So we have four-wheel drive here, front-wheel drive, and rear-wheel drive. And then groups the data based on those drive types. So here's our four-wheel drive mileage, and here is our rear-wheel drive and our front-wheel drive. So you can see here by this plot that it might be a valid assumption, say, that the front-wheel drive cars get better mileage, which kind of makes sense because on our previous facet grid, we saw that the cars with a smaller number of cylinders have a higher concentration of front-wheel drive models. So we've seen how ggplot will automatically group our variables based on levels. And here's an example for doing it explicitly using the group aesthetic. So we've got the group argument we're providing, and we're basing it on the values of the drive variable. Normally, though, we want to visually distinguish between the levels with colors, line styles, or other settings, as we've done in previous slides. So here's an example where we're mapping that drive variable to the color aesthetic. And again, ggplot automatically determines the colors to use and provides a legend on the right for each of the different drive types. Now, we demonstrated previously that we could put the X and Y mapping either into the geom itself or put it into the plot function, which we're doing again here, just to demonstrate that this vastly simplifies our geom statements. So it takes the X and Y values used in the plot function and applies them in the additional geoms that we add here without having to re-specify them in the parentheses. So let's jump over to RStudio and play around with some of these plot commands. So we saw how we could do our plots, mapping the X and Y values to the displacement and highway mileage, and then we brought in the class variable and mapped that for the class of vehicle. We can do this with any of the categorical variables in the data. So for instance, if I do the ggplot and specify my data, I'm going to map the manufacturer to the displacement and highway data to see if there's any apparent impact on the manufacturer of the vehicle for a mileage. So if I do geom point, and my mapping is X is displacement, Y is highway, color, I'm going to map to the manufacturer variable. So you see we get all these different manufacturers, and the color mapping pretty cluttered, a little hard to tell really, but you see that we have for the higher mileage some of the typical manufacturers of smaller cars. So we have Toyota up here, and we have what looks like the Hyundais here on the left with the smaller engine size getting the higher mileage. Now we would probably want to dig into the model numbers. For all we know, the Fords and the Dodges here are muscle cars. So we'd need to dig into the data and find out really what the models of those cars were. But this is just another way we can map a third variable into our plot. So now let's reformat this using facets. Instead of doing all these colored points jumbled together, we'll split it out. So I'm going to do a ggplot, my data, and do a scatter plot and give it my X and Y. Then I'm going to add a facet wrap where this breaks it out into subplots and use my manufacturer. And so now this splits it out by manufacturer for each subplot, and we can see if we look for the higher levels, we see the Honda, the Hyundai, the Toyota, Volkswagen, whereas the typical larger model cars are down here with the Chevrolet and the Dodge and the Ford. This helps make it easier to read. And we can change a variable. Let's change, instead of doing highway, let's look at city mileage. So that's just a change of replacing highway with city. We run it again. And we see, looks like about the same results. It'd be nice to do a side-by-side comparison. So let's look at how we might do that. Let's do a line plot, specify our data, and now I'm going to use geom smooth to do a smoother, and my mapping AES, X equals displacement, Y equals city, Now I can layer, remember these are layering these geoms, so I can layer another geom on here, and I'm actually going to duplicate this geom smooth. So just copy and paste it and tack it onto the end there, and I'm going to replace the city in this one with highway. And now if I run this, notice it gives us a little heads up here as for the method for the smoothing operation that it's doing, and then the formula. And this is just normal. There's nothing wrong here. It's just giving us a little more information. And we get these two curves. And so we see one of them is providing better mileage than the other, but we're not distinguishing between the two. We have the label on the left, which is indicating city, and that's not distinguishing between highway and city. We'd want to adjust that label, but let's make the geom distinguish itself for city versus highway by using a different aesthetic. So what I'm going to do here is I'm going to add to this second geom smooth with the highway mileage a line type, and I'll just give it a 2. Remember, we have these numeric values that refer to different types of aesthetics, and so for the lines it refers to a long dash line. So if I run this now, you'll see we get the distinction. So the higher level line is the highway mileage, and then the lower is the city mileage, based on mapping the engine size, which is on the x-axis here. So this is a good way to show that the ggplot, we could just layer more and more information on these plots and make them more useful for us. Now when we put aesthetics into a geom, they're treated more or less like local variables, local settings, and they only apply to the geom where they occur. So here we're adding the color equals class aesthetic to the point geom, so it doesn't impact the smooth geom, and it's just basically a local setting for each specific layer that we're adding to the plot. We can isolate our levels with a filter function within a specific geom. So here we're asking ggplot to map the subcompact class with a smoother in our plot, and so you see we get a single smoother here. And if we look at the color codes, we would see that the blue, it's a little difficult to see here, is our subcompact class. And we have this additional argument for the SE, which refers to the confidence interval. We can turn this off because otherwise you get a shadowed line like we've seen before with the confidence bands on our line plots. So if we want to shut that off, we use this SE equals false, and that will avoid the display of those confidence intervals. Chapter 2 is a very short chapter that covers topics that should mostly be review for us. There's a couple easy exercises at the end of the chapter you can take a look at. If I scroll through this online version of the text, you can see it covers workflow, coding basics, variable names, object assignments, how to call functions. So again, this is all review for us. These exercises, why does this code not work? This one is kind of weird. You can see that I think what they're trying to get across here is they're just misspelling the object name my variable with this, which I think is a lowercase l or the number 1. Not sure because it's a different font, so it looks kind of strange. But what I believe they're trying to say is you have to spell your variables consistently, which is nothing new for us. So that's an easy one. Tweak each of the following R commands so they run correctly. So we have loading the Tidyverse, and then we do a ggplot. And you'll see here that they've misspelled the named argument data and misspelled filter. And so we have these just basic, mostly syntax errors that they're showing here. And then Alt-Shift-K, well, you can try it in RStudio. What happens when you do Alt-Shift-K on a PC, Alt-Shift-K brings up the keyboard shortcut reference. And so you have all these keyboard shortcuts. If you're a big keyboard person with RStudio, then these will help you do your keyboarding more efficiently. So just read through chapter 2 and make sure you have a handle on all that stuff. It's a very, very short chapter. Now we're going to get into dplyr, which is a Tidyverse package we can use to manipulate and transform data. So the dplyr package provides functions that usually act on data frames or Tibbles, and we'll see that we use them interchangeably quite a bit. The package is designed for performance with those types of objects, and they also have a way to transparently access a relational database, which is pretty cool. If you have the appropriate backend loaded for your particular database type, you can run the dplyr code and have it accessing a database as opposed to local data in a file, for instance. And one of the primary design philosophies of dplyr is simplicity. So the functions are what I would call single-minded. Each function is designed to do one thing, but to do it very well. So let's do some work with dplyr using the NYC flights dataset, which is included in the package. This is airline data for flights departing New York City in 2013. Also includes some metadata describing airlines, airports, weather, and planes. So to load it, we have to make sure we have dplyr loaded first, and then we run the library command, and then we can run the library for the dataset to bring it in. Now you may see some conflicts when you're loading dplyr because it masks some of the base R functions. And we talked about this in a previous module. So you'll see warnings like this, that the dplyr filter function is masking the stats filter function. So if you need to use these base R functions, you just use the fully qualified name. So you provide package name, which in case of the filter function is stats with 2 colons, and then the filter function name when you call it. And that's how you can access those masked functions. Our NYC flight data is a Tibble, and it's pretty sizable. There's over 300,000 observations in it with 19 variables. And we have the columns, and these are all going to be 2013, of course, for the year. But we'll have varying months and days, departure time, scheduled departure time, and then the remaining variables that we can't see here. We've already seen some of these data types in the earlier Tibble we looked at. We saw int, we saw the character. We've also got these abbreviations for the types in the Tibble. We have double for doubles or real numbers. We have a date time, which is a POSIX CT object. We have LGL for logical, which is the Boolean true false values. We have factor, FCTR, which represents our categorical variables and possible values. And then we have dates. If you want to see the entire data set, you could just use the view function. That's uppercase V with view, and then the name of the Tibble as it's been loaded. And so you see flights and you see all the rows, and then I'm just collapsing these so we don't have to scroll through all this stuff. But this goes to the right with the remainder of the variables, and you can scroll down all the way through all 300,000 plus records of this data if you run this function. So there are 6 basic functions on dplyr. We can filter observations by value. We can reorder rows. We can select variables by name. We can create new variables based on existing ones. We can perform aggregate summary functions, and then we can group our data and perform any of the above functions on those groups. To use filter, we provide the object, the data frame or the Tibble, followed by any variable names we want to select. So it's like a selection, like an extraction. And so in this case, we're selecting all the flights that occur on the 1st of January. And you see it reduces our data set. We had the 300,000+ observations and 19 variables. And now we've reduced that to 842 observations. And we're using the double equals for the comparison of the values. Now, filter doesn't modify the data we pass to it. So when we pass the flights Tibble to it, we don't modify that. We return the results. And so if we want to save the results, we need to assign it to a new variable. So here we're assigning it to this January 1st variable. We can also wrap the entire expression in parentheses. In that case, it'll both display and save the results to the console. R uses IEEE 754, just like most other programming languages. So when you compare, you're not going to be getting an exact result when you're using floating point values. So here we are calculating the square root of 2, which is an irrational value. And then we're squaring it to try to come up with the original value of 2. But because of the representation internally of our floating point values, that is not equal to 2. It's off by some very, very minuscule significance, but it's still not equal. Same thing if we divide 1 divided by 49 and try to multiply it by 49 to return back to the original value of 1, we don't get that result as expected either. So instead we have a function called near, which is basically looking at the significance, and if it's close enough, then it's going to return true. And so if we run square root of 2 and square it and compare it to 2, the near function says, okay, that's close enough for us, and it returns true. Same thing for multiplying 49 times 1 over 49 and comparing it to 1, it results as true. Now, if you want to get the details, just run a help on near to find out the details of how it's working internally and more information about the significance. We already covered missing values in an earlier module. Remember that they can propagate through our data. So if we have NAs in some original data, they basically will follow all the way through, and we can end up with results that are also as NA. So we have to be cognizant of that when we're working with our data. With the filter function, we can provide the is.na as part of the condition for the values we're filtering. In this example, we have a data frame we're creating, just a very simple one of 3 rows with 1 column, and we provide an NA value just to kind of force the issue, just to demonstrate this. And so in this case, we have the filter function. We're filtering df for the value of the column x greater than 1, and we get the value 3, which is the only value, if we don't include the NA, that's greater than 1. But if we provide a logical OR is.na of the variable x, or x being greater than 1, then you see we can include the NA in our results if we want to do it that way. The arrange function basically is a way to reorder the rows in our data. The arguments we provide act like sort keys. So here we're providing our flights tibble, and we're saying sort it on the primary value of the scheduled depart time. And so we don't see all the rows here, but if you were to look at all the rows of these observations, you would see that this field, the scheduled depart time, is being used as a sort key, and they are all ascending, and it'll reorder the rows that are associated with each of those values based on using that value as a sort key. And then if we have secondary keys, provide additional variables. So the year is the next key to use for the rearranging of the rows, but we know that this is all 2013 in this data set. Then we go to the month. And so if we have any rows that are grouped based on our scheduled depart time with the same value, in other words, if we have a bunch of 500s, it's going to sort as a secondary key using that month value. So you see this starts with 1, and any subsequent 500s would continue to go in ascending order 2, 3, 4, 5. Whereas the 106, that's the only row, that's the only observation with that departure time. So we only get 1 value for the month. So no subsort of those rows is necessary or occurs there. But for this one where we have multiples, it will use that secondary key. And then if there's a tie in the months, it sorts the days. So you see here for all these months of January, the days are also sorted in secondary or as a subsequent ordering. If you've ever used Excel, they provide these sort orders like this, where you have a primary sort and then subsequent columns are used for secondary sorts. If we want to sort using arrange in descending order, we have a descending function we can provide. So this is calling arrange with flights, but we're saying sort it by this variable departure delay in descending order. So now if we find the departure delay column over here, we'll see that it starts with the highest value and works its way down to the lowest value. And then all the associated rows are going to be carried along with those rearranged rows based on that sort key. When we use arrange with missing data, the missing values are already included at the end of the data. So here again, we're creating a very simple tibble of 3 rows and 1 column and inserting an NA at the very end. We can see it displayed here. If we sort it by X, which is going to sort in ascending order, it's going to switch 5 and 2 here, and it does, but the NA stays at the bottom. So we keep those at the end. If we say go in descending order, it basically just puts it back in the original order, where 5 is first and then 2, but the NA still is left at the end. The select function lets us do a subset operation. So here we're calling select with our flights data, and we're specifying that we want the year, month, and day variables. So we get the same number of observations, but now we only get those 3 variables that we specified here. You see this based on the display of that tibble, and it does create another tibble, or if it was a data frame, it would create another data frame. If we want to exclude instead of do an inclusive operation with select, we can use the minus sign in front of the variables we're interested in. In this case, it's a sequence or a range from year to day. So it's going to eliminate year, month, and day from our result, because month occurs between year and day in the original ordering of the columns. And so now we've reduced our tibble by 3 variables. It's 16 instead of 19. We still get all of those rows. And when we use select, there's also helper functions available to do pattern matching. We have a starts with, an ends with, and a contains. So this helps us decide what we want to include when we do the selection. We also have this everything helper. So if we want to specify a certain number of variables, in this case we're requesting the scheduled departure hour and the scheduled air time, and then we're saying after that selection put everything else. So we get the remaining variables here, but it reorders the variables by our specified ordering here. So time, hour, air time are first. We still have all 19 variables that are going to show up. I'm not showing them here, but we still do have all 19 variables. It just plugs everything in after those columns. So this is more or less like a store operation for the column or the variable ordering instead of the rows. Summarize is an aggregate function. We can apply aggregate statistical functions to our data. So in this case, we are passing flights to summarize, and we are calling the mean function with the departure delay variable, and we're assigning that result to a new tibble called delay. And you see we end up with a 1-by-1 tibble, which is a summary value of the mean of all those columns. And we also have this na.rm argument that I'll talk about in a few slides here. What it's doing is it's removing the na values from the data before it calculates the mean. So group by creates subgroups of data that we can individually analyze. In this example, we're organizing the observations by date. So we're using a combined value of the year, month, and day variables to create a group, and we're assigning the result of that operation to this by day object. We're passing that grouped object to the summarize function and doing the same operation we did on the last slide, calling the mean, removing NAs, but instead of doing a single aggregate mean, it's using the groups. So it's doing average delays for each day. So when we grouped by day, year, month, and day here, it created 365 individual days of 4 variables, the year, month, the day, and then the delay, which was a result of calling the mean function on all those groups. So we get the mean of each day for our delays here. At this point, we need to introduce the pipe operator. This operator is specific for the Tidyverse, but it works like pipe operators in various operating systems, if you're familiar with those, Unix in particular, where you pipe results from one operation into a subsequent operation. So these lines here demonstrate the basic difference between not using a pipe and using a pipe. We might call the filter function and pass our data and then specify our variable values here for the filter. But, and this is a very trivial example, we could take our data, which is our flights tibble, use this pipe operator, which is % greater than %, no spaces between them, and pass that data into the filter function. So you see there's no variable here that we're passing for the data argument. We're passing it in through this pipe operation. And again, this is something specific to the Tidyverse. Base R doesn't have this, and then we continue on with subsequent arguments. So both of these functions work in the same way, same results, but when we have multiple functions we're calling, the pipe operator will make it easier. It'll make a simpler expression out of it. As an example, we're going to do all these operations without a pipe: filter, group by, summarize, arrange. So for each one, we're starting with empty cars for our data set here. And we've got the condition of carb is greater than 1, and we're assigning it to an intermediate variable A. Then we pass A and assign the group by result to a variable B. We pass B, assign the summarized result to C, and then pass C to arrange, and the final result is D. This is a way to do this sequence of operations, but using a pipe here is how the pipe simplifies that. We pass our data using a pipe into the filter function. That's the first function that occurs here. We only specify the condition. We don't need to specify the data argument because that's coming in from the pipe. The result of that is piped into the group by function, which is piped into the summarize function, which is finally piped into the arrange function. And the arrange prints out the results. We don't need the print operation here in a descending order. And so this set of lines here is the same as executing these 5 different statements. So you can see that this simplifies these operations by using this pipe operator to pass the intermediate results without having to create variables for each one of them. So you'll see this in a lot of the Tidyverse operations we use. Notice the formatting. I've indented everything after the initial data set specification. And I put the pipe symbol at the end, which indicates there's something to come on the next line. And we just follow through with each line. Kind of like an if statement here, where everything inside the if is indented. It makes it easier to read. We don't really care about how the pipe works under the hood. You can definitely research and get more information on it, but in a nutshell, it just creates a bunch of nested function calls. And because we can write these in a nicely formatted and organized manner, one of the primary benefits that we can see of pipes are readability of code, which is very important when we get into more complex expressions and more complex scripts. I mentioned values already, and I mentioned the na.rm. This is just kind of a reminder slide here that if there's any missing values in the input, then we're going to get missing values in the output. So if we have NAs in our flight data, and in this case we're doing a group by and summarize with the mean, then we're going to get NAs in our final grouped data as well. So this is where that na.rm argument comes in handy. It cleans up our data for us and removes the missing data before it tries to do the calculation, and then we get valid results in our final calculations here.